We begin with a data contradiction, a claim from a senior Apple executive that fundamentally challenges how we measure computer hardware.
This statement right here is the subject of our entire investigation. It posits that the physical laws of memory capacity somehow operate differently inside Apple's ecosystem. Our task is to determine if this is fact or if it's friction.
So which is it? A genuine architectural breakthrough or just a very sophisticated piece of marketing? To resolve this, we have to conduct a forensic examination of the architecture, the hard performance data, and of course, the economic trade-offs for you, the end user.
Okay, Act 1, the architecture. To really understand the claim, we first have to deconstruct the two competing designs at a structural level. That's the traditional modular PC versus this integrated, unified system.
Think of a traditional system's memory like two separate water reservoirs. You have your main system RAM, and then you have your graphics VRAM. To move data between them, the system has to physically copy it, carrying it across the PCIe bus. It's redundant by design. The Unified Memory Architecture, or UMA, collapses this into a single, shared lake of memory, eliminating the need for those inefficient copies.
This is achieved through a mechanism called zero-copy access. Instead of moving the data, the system just points all the different components, the CPU, the GPU, the neural engine, to the exact same block of data in that shared lake. This creates an incredible volumetric efficiency. So if a traditional PC needs 8 gigabytes for a task because it's duplicating 4 gigabytes of assets, a unified system just needs the original 4 gigs. That's it. This right here is the technical foundation of Apple's claim.
And this efficiency is paired with a massive increase in bandwidth, basically the size of the pipes moving data out of that lake. As you can see from the data, high-end UMA memory bandwidth just blows standard PC system RAM out of the water. This incredible speed allows the system to fetch and discard data so rapidly that it creates a perception of fluidity, a feeling that for short burst tasks can mask a lower physical capacity.
So that's the theory. But what happens when that shared lake runs dry? Let's examine the system's primary defense mechanism when its physical capacity is exhausted. Every modern operating system has a safety net for when it hits a memory drought. It's called virtual memory, or swap. When the physical RAM is completely full, the system writes the least used data to the internal storage drive to free up space. This buffer is what prevents a system crash.
But this buffer is not without cost. Its function is governed by a very clear process of decay. First, it serves its purpose, maintaining system stability. Second, there's a degradation rate. Each write operation consumes a tiny fraction of the SSD's finite lifespan. And third, and this is the most critical part for performance, you get hit with a severe latency penalty. You're moving from the nanosecond speed of RAM to the microsecond speed of an SSD. That's a 1,000-fold delay.
The pressure on this buffer in low-capacity systems is substantial. Let's take a real-world example, a remote office administrator. They're running multiple browser tabs, communication apps, a few spreadsheets. Under just this moderate load, an 8-gigabyte UMA system can write up to 1 terabyte of data to its drive in a single day, purely from swap activity.
Now, the immediate concern is hardware failure, but the math doesn't really support that. For a standard drive rated for 300 terabytes written, this level of swap still projects a lifespan of nearly 9 years. Catastrophic failure is a statistical improbability. The true cost here is not physical, but a systemic exhaustion of performance.
Act 3, the workload verdict. Now we're going to subject that equivalency claim to an empirical stress test, moving from architectural theory into the physical reality of professional workloads. Okay, look at this. We have two architecturally identical machines performing a professional video render, a highly time-sensitive task for a freelance content creator. The only variable is the memory. The 16-gigabyte system finishes in about 5 minutes. The 8-gigabyte system, it needs over 20 minutes. For that freelancer, this delay directly impacts their billable hours. This performance deficit, we're talking nearly 300%, is the direct measurable cost of relying on that SSD buffer. It's the new friction. For that editor, this isn't a marginal difference. It is the friction that defines a productive versus an unproductive workday. The laws of information theory are absolute. 8 gigabytes of physical space cannot store 16 gigabytes of incompressible data.
So let's pause. This is the cognitive landing.
The architectural efficiency of unified memory is a physical reality. That is a fact. However, its performance benefit is entirely contingent on the workload. The very definition of better is determined by the specific task being performed.
And this table makes it perfectly clear. No single architecture is superior in all cases. If you're a software developer running virtual machines, your governing constraint is raw physical capacity. A traditional PC with 16+ gigs of RAM is simply better. But if you're a generative AI researcher running a large language model locally, your constraint is memory bandwidth and that pool size. A high-capacity UMA system has an insurmountable advantage.
So we can now make a probabilistic forecast. Let's start with the base case. This applies to the majority of users. For light multitasking, an 8 GB UMA system will feel incredibly responsive. Its efficiency with compression and swap is so good that honestly, the 8 = 16 claim will seem plausible under these conditions.
But then there's the tail risk. This is the low probability, high consequence outcome. It applies to the professional user who pushes the system to its physical limit. Under that sustained load, the system experiences severe performance degradation, rendering it functionally unsuitable for the very pro tasks its branding implies it can handle.
Okay, Act 4, the final ledger. Let's summarize the permanent trade-offs and identify the key metric to watch for the future.
The architectural ledger is clear. Unified memory offers superior efficiency and bandwidth. The cost? Zero future upgradability. Traditional architectures offer modularity and raw capacity. The cost? Latency and data duplication. The ultimate price of this trade-off is paid by the consumer who incorrectly forecasts their future needs at the moment they buy the machine.
And the marketing claim of direct equivalence between 8 and 16 gigabytes, well, it significantly increases the probability of this user miscalculation. It creates economic friction.
Now, we are seeing the market's immune response. The disruption from UMA, especially in AI, has forced competitors to adapt. Microsoft is mitigating the old bottleneck with software, while AMD is now producing its own unified memory architecture. This proves UMA is an evolutionary step, not some proprietary anomaly.
And this gives us a falsifiable horizon. The key metric to watch going forward is the performance per watt of competing UMA platforms like AMD's Ryzen AI Max, specifically when it's running local AI inference. That number will tell us if this architectural advantage can be fully commoditized.
So, in the end, it comes down to this. The architectural efficiency is a physical fact. The direct capacity equivalence is a marketing fiction.